Good morning. This is lecture number 14, Analog Microelectronic Circuits, and we are discussing MOSFET-based amplifiers from the previous class, and we were solving one numerical on the CS amplifier. So we completed the first part, the DC analysis part. We obtained the drain current. We also obtained the small signal parameters GM and R0. Now, if you look at the rest of the question, you are also asked to calculate mid-frequency gain and the maximum allowed input signal to this particular amplifier. So, I hope you remember when we started, we took only the DC part, that is only with the biasing, and we arrived at the GM and R0 values. So once that is done, so why we have taken this is because the capacitive reactance is very large at DC. That means there is no DC current flowing towards the input or the output side. So since the capacitors act as open circuit or capacitors reactance is very large, we will consider only this part for the analysis, which is given in blue. Now, in order to find the gain, so I'll explain what is this mid-frequency gain V0 by Vi, V0 by Vs, and how to calculate that. But just before that, let us take that part of circuit where, or let us consider the circuit as a whole in order to do this small signal analysis, right? So we call this as the so I hope you remember we have done as two headings or two steps. The first step was actually to do the DC analysis, that is done, and now what we are doing is the AC or small signal analysis. Small signal analysis, or we call this as AC analysis. So when you talk about small signal analysis or AC analysis, we are considering the signal component also. When you say signal component, which is having some certain frequency. Now, now then one thing to remember here is, previously I have taken as capacitive reactance XC as 1 by 2 pi FC, and for DC this capacitance seems to be very large, and it acts as open circuit, so it is infinity, and that led to open circuit. Now for AC analysis, what we are considering is we are considering that the capacitive reactance. So AC analysis is in some frequency. We are considering some frequency, and we call that as mid frequency. Mid frequency is not towards the very high range, not towards the very low range, but for mid frequency or a set of frequencies, we consider that the capacitance for mid frequency 1 by 2 pi FC. F is not 0, F is a large value, probably we can assume in mega ohms or something. So we assume that this value, so as F increases, capacitive reactance will definitely reduce. And for mid-frequency analysis, we will consider the capacitance act as short circuit. The reactance will be small. It is not 0. Reactance is definitely small, but we consider it as short for the ease of our analysis, right? So for mid frequency, so this is I'll write in brackets for mid frequency, because what we are looking at is an analog circuit. Definitely that will not go for very high frequency. Then if it is an RF, if it is going towards very high frequency in gigahertz or something, then we have to look for different circuits. Now this CS amplifier what we have discussed just now cannot be used for gigahertz range, right? So that is why we call this as mid frequency. Mid frequency in the sense mid in the spectrum. When you consider low and high, this is somewhere mid in the spectrum, and we assume that the capacitive reactance is short. Now capacitance, if it is acting as short, and if I draw the rest of the diagram, so I have MOSFET, then I have to consider the resistances, the resistance over here. This is what we have considered before. This is VDD. Now what we have taken here is all the capacitances are acting as short. That means input side you have a short. I will replace the capacitor with a short, and then we will keep the other resistor there, and we will provide the signal here. So this is Vs, and this is supposed to be 25 kilo ohm. This is 390 kilo ohm, and this is 1210 kilo ohm. Here is it is 15K. Now, if you look at the output side, there also one capacitor was there, and that also will act as short. And now this we will um, put as 60K here, and this is V out. Now, if you look at this terminal here, also there is a capacitor. So a capacitor should be replaced by a short. That means something like this, right? So that makes some difference here. Up, compared to the other capacitors which is there on the input side, at the gate and at the drain side, this capacitor when we make short, even the effect of this resistance also will get nullified, because there is a short across the resistor that is as same as having a short here. The resistance will not have any effect, because even if there is a current that will flow directly from this point to ground, not through resistance, because of the shortest resistance or the smallest resistance or a short circuit path. Right. So these are the changes what I need to do here. And one more change is, as we discussed before, since it is AC analysis, since it is small signal analysis, no need to consider DC. That doesn't mean that DC is zero. DC is there, but since we are looking for a small signal circuit where we are looking for uh, looking for signals which is having incremental change, or signals which is changing, since DC is not a changing one, we will keep it as short. So I will make a note here. One is, all capacitors are replaced with a short. So that resulted in what? So therefore, the RS resistance is removed. Why it is removed? Because there is a short circuit across it. Now another important thing is, VDD also will be replaced by a short circuit. Why? Because it is not a changing voltage. So that we have considered even here when we discussed that. Where did we discuss that? Yeah. So whenever we do small signal analysis, we will nullify the effect of DC sources. Now, what I have here is again a DC source. VDD is a DC source. So this will be the equivalent circuit. Are you guys with me? Are you? Did you get this? What I have done? Can I get some response in the chat box? Are you guys with me? All right. Others? Yeah. So two things to note here. One is, you have to replace the independent sources, the DC sources, with a short, since again with the understanding that even for small signal operation DC is required, but for the ease of our analysis, when we look only at the small signal or the varying components, no need to consider DC. DC we already considered. Second thing is, all the capacitors should be replaced by a short, assuming that at mid frequency the reactance offered by the capacitance is very, very small, and that resulted in the removal of the resistance RS. Right. So with this, what I will do now is, I will just draw the so now if I want to analyze for the small signal equivalent circuit, I should replace MOSFET with its equivalent. Right. So what is MOSFET's equivalent? So let me draw the three terminals here, 1, 2, 3. This terminal being source, this being gate, and this being drain. Like this only we should start doing. Now we know that, so first I'll draw the, probably I'll use a different color for here. Since it is MOSFET, I will use a different color just to identify between the components. So this is your gate, this is drain, and this is source. Now when you apply a VGS here, this as VGS, you will actually get you can represent MOSFET using a current source of GM-VGS, and with channeling the modulation we can have this as R0. So channeling the modulation we need to consider, because VA, some voltage is given. I stated that that is early voltage, and that is related to lambda as 1 by lambda. Now this is the equivalent of MOSFET, right? Now we have to modify this equivalent circuit depending on the given circuit. So what is the given circuit? Now let us look at the circuit. What about source terminal? Source terminal is directly grounded, so I can actually ground the source terminal here like this. Now look at gate. At gate you have one resistance from gate to VDD, that is VDD is ground now. That means you have a resistance of 1210 from gate to ground. That means I can do that. One resistance from gate to ground, that is 1210K. You have one more resistance from the same point to ground, that is 390K, another resistance. So either you can draw two resistances, or you can write one resistance and give the value as 390K parallel to 1210K. Now again from the same point you have 25 kilo ohm resistance. So I will draw that 25 kilo ohm here from the same point, and to the other side you have the signal source connected. So that is Vs. Right. So this is what you have on the left hand side or towards the gate side. Now source is grounded anyway. Now when I look at the drain point, this is drain point. What are the components there? 115K from that point to VDD. VDD is now ground. So I have to connect a resistance there of 15K from that point to ground. Again from the same point you have another 60K resistance from there to ground. So this is 60K. As I mentioned before, you can draw one resistance and put the equivalent resistance as 15K parallel to 60K, and this is the V out node. This is the V out point. So now this is the equivalent circuit. Right. Now with this equivalent, so with this equivalent, let me take this equivalent circuit and let me place this in the next page. Right. So this is the equivalent circuit now. I hope this is clear for you guys. If you have doubt in any of the component what I have drawn in the equivalent circuit, please you can ask now. Otherwise, I will proceed with the calculations. All right. So if you have doubts, then also I can consider that at the end. Now, on this equivalent circuit, I'm just marking one more point. So if you look at the question, you can see that there is something called as the maximum allowed input signal is Vi. So that, sorry, I didn't mark that in the question. So it is marked at this point. Even in the question, it was given Vi is somewhere at this point. So the same thing I'm marking here, Vi is actually at the gate point, which is equal to this. This is Vi, or Vi is equal to VGS value, right? Now, we will, so what we have to do now is we have to find the mid frequency gain. What are the quantities given? We have to calculate both V0 by Vs and V0 by Vi, right? So V0 is nothing but V out here. So you can use one notation throughout, either it is VO or V out. It is V out only everywhere. So I will consider it as V out only. Yes. So this is V out. Now you can see that V out is output, but at the input side there are two voltages marked. One is Vi and another one is Vs. Right. So one thing you can observe here, probably this I will replace with a single resistance. That is easy for us. And can someone of you tell me what is this value? What will be this value? 1210K parallel to 390K. Can I get this parallel combination value? What is 1210K in parallel to 390K? Yeah, so while you guys are solving that, I'll just put this as R signal and this as R1 parallel R2 and this as RD and this as RL. So let me write the, all right, 294.93. So this is equal to 294.9K. All right. Okay. Now, so what I'll do first is I will try to find a relationship between Vs and Vi. That means I'll look only at the input side first. So if we look at input side, you have Vs voltage here. Now from Vs voltage, you have a 25 kilo ohm resistance, 25K, and from the other one resistance, which is R1 parallel to R2. Instead of 25K, I will write this as R signal. Now this is Vs and this is Vi. So can you tell me what is the relationship between Vs and Vi? There is no current flowing towards here because it is an open circuit. So the only current flowing is actually here. So this is as simple as a voltage divider. So Vs voltage is available at Vi as, how will I write Vi? Vi is equal to the total voltage Vs into R1 parallel R2 divided by R signal plus R1 parallel R2. This is a simple voltage division. So how will you arrive at this? You can actually write a KVL by considering current as I. It is a considering current as I. We'll consider small I, right? And from that from this current, I can write Vs minus I into R signal minus R1 parallel R2 into I is equal to 0, or that itself is equal to Vi, and you can get this equation. That is the, I think that is straightforward, and I hope you guys are following this. So this is on this side. So now from this, what I can write is, I can write what is Vi by Vs, and that is equal to R1 parallel R2 divided by R signal plus R1 parallel R2. That is done. Vi by Vs. Now, I look at the output side. So how to write what is V out? I can write V out. V out is actually the voltage across resistance RL. That will be same as voltage across resistance RD. That will be same as voltage across resistance R0. Right. So instead of writing three resistance here, I can consider all these three resistance are in parallel. So it is R0 parallel RD parallel RL. That is the equivalent resistance. Now how to write voltage? Equivalent resistance multiplied by current. What is the current here? The current flowing towards this side is GMVGS. Now, so what will be the current flow? So current is flowing in the opposite direction. So you have to put a minus sign. And so minus GMVGS into R0 parallel RD parallel RL is V out. Now what is VGS? VGS is same as VI. VGS is same as Vi because Vi is again marked at gate with respect to source. Source is ground. So I can write V out as minus Gm into Vi into R0 parallel RD parallel RL, or from this I can write what is V out by Vi. What is V out by Vi? Which is equal to minus Gm into R0 parallel RD parallel RL. So that is your first question. Find the mid frequency gain V out by Vi. So if you substitute the value for Gm, R0, RD and RL, you will get the answer for this. You can do that. Let me complete. So one more question is asked. What is V out by Vs? So how will I get V out by Vs? V out is directly related to Vi and Vi is related to Vs. So I will write V out by Vs as V out by Vi, that is the voltage here and the voltage here, into Vi by Vs. So I can write V out by Vs as V out by Vi into Vi by Vs. Now I know what is V out by Vi and I know what is Vi by Vs. So together if I write V out by Vs, it will be equal to, yeah, whatever. It will be the product of these two. So V out by Vi you will get from here. That should be multiplied by Vi by Vs, which is another factor here. So this also you will get an answer for this V out by Vs. Right. So now I request you guys to get the numerical value for this by substituting all the parameters. Tell me what is V out by Vi and tell me what is V out by Vs. So if you write the expression for V out by Vs, R0 parallel RD parallel RL multiplied by R1 parallel R2 divided by R signal plus R1 parallel R2. So can I get answers for V naught by V out by Vi and V out by Vs? Probably you can find what is Vi by Vs first and then you can do the rest. Are you guys with me? So I wanted to know the value of V naught by Vs and V naught by Vi. So this sometimes this we call it as AV and this we call it as AV with respect to source. V naught by Vi is minus 10. Yes, V naught by Vi is minus 10. V bar V. You don't get confused. The units will be volts per volt, but that is same as writing it as a dimensionless quantity. V naught by Vi is minus 10 and V naught by Vs is minus 9.2. V naught by Vs is minus 9.2. So others also, yeah, I'll wait for you guys. You can just work out. So what I'm trying to say here is V naught by Vi is in fact minus 10, but V naught by Vs, if you consider, there will be little more, there will be a small drop because the drop is because of this voltage division happening here, right? So your V naught by Vs is V naught by Vi into Vi by Vs, and this Vi by Vs is actually a quantity which is lesser than 1. Right. Vi by Vs is 0.92. Yes, thank you. 0.9219. So which is not equal to 1. It is slightly lesser than 1 because of the voltage division. That is why you are getting a lesser value for V naught by Vs. Right. Okay. So you guys can try out. So don't get tension. So calculate one by one. You can actually do the calculation based on what I have done here. Maybe you can find what is Vi by Vs first. Then only thing is you have to get the equivalent resistance of R naught parallel Rd parallel RL, and that can be multiplied with Gm. All the values are already there with you. Right. So one more thing is there. If you look at the last part of the question, it is also asked what is the maximum allowed input signal Vi. So what can be the maximum value of the signal? Value in the sense it is asking the peak value or the amplitude that can be given to this node. So maximum allowed in the sense if you are giving more than that, the transistor will leave or move out of saturation. That is a condition. So listen carefully. This is important. So maximum allowed input signal. So to find the maximum allowed input signal, any doubts in between? You have any doubts? All right. So the maximum allowed input signal can be obtained by the condition for saturation. So what is the condition for saturation? The condition for saturation is VDS should be greater than VGS minus VT. This is the condition for saturation. Now we know that it is not only DC here. You have now DC and an AC voltage. So instead of writing it as VDS, we will write it as VDS, which shows it is a composite signal. You have DC and AC. I'm looking at the input signal just to know the biasing also. So this VDS should be greater than or equal to this VGS minus VT, right? So this shows that you have a signal which is your signal is not on 0 or some other level. Your signal is on a DC level. How to know the DC level? So the DC level, so this VDS is in fact VDS plus VDS greater than or equal to, you have a DC level, on that you are applying a signal minus VT. Oh, this is the condition, right? Now so to understand this better, so now in the question what is asked, what is the maximum allowed input signal Vi? What is that maximum allowed input signal Vi? Vi is a signal at the gate. That means the question asked, or this is your Vi component, the signal at the gate Vi. Now how to get VDS? VDS is a signal at drain. So how your input and output are related? So if input is Vi, your output is related to input as A times Vi, right? It is always related as A times Vi. Now what is the case here? We have seen that your gain is minus here, right? So I am just writing this VDS as A times Vi, but we know that say this is your transistor, this is your entire circuit. Now if you're applying a signal in this form, as I explained in the on the other day, your output signal will actually grow in this direction. So it will be growing towards negative direction when you have a positive increment, and it will be going towards the positive direction when you have a negative increment. This is the condition, right? Now that means when this is Vi, what I'm getting at the output is A times Vi, but since A is actually negative, so you have to consider that negative either by putting an explicit negative sign, or you have to consider the negative sign of the gain itself, right? So what I'm writing here is so at the input you have a DC level, that DC level is VGS. Output also you have a DC level, that DC level is capital VDS. Now on that DC level of output VDS, so I'll write this as VDS, but your signal is actually going in the opposite direction, so I'll put minus magnitude of A into Vi. So either I can write VDS plus AVI, either I can write VDS plus AVI and substitute A for negative, or I can write VDS minus magnitude of A into Vi. Any way is okay, greater than or equal to VGS plus Vi minus VT. Right. So in this, you are asked to find Vi. You know what is VDS, you know what is VGS, you know what is VT, you know what is A. Then you can find what is Vi. So can I get the value for Vi? The question asks this maximum allowed input signal. So what can be the maximum input signal I can provide here such that the transistor will still remain in saturation? For that I have taken the condition for saturation, but I know that now I have a signal also. So instead of writing the condition just for DC, I have modified the condition for AC plus DC as this, and there I have splitted it as DC component and AC component, and I have replaced the AC component VDS with A times Vi, or it can be replaced as minus of mod A times Vi. Substitute VDS, VGS, VT and then get the value for Vi. So how to get VDS? To get VDS you have to, so to get VD you have to write it as 16 minus the current value, 16 minus 15K into ID by considering ID in milliamps, and Vs will be equal to 6K into ID. Vg I think we already calculated in the beginning. Vg value is 3.9. So ID is 0.4 milliamps. So with that you will get these values. Can I get the value of Vi? Can I get some answers in the chat box? Vi is 0.618. Any more answers? Please understand the notations here. The full small letters are AC, full caps are DC, and the combination is composite signal AC and DC. So can I get the values of VD, VS and VD and VS? What is VD? 16 minus 5K into ID. So what is the VD value? VD is 10. Okay. What about VS? VS is 2.4. All right. So again, you can see that it is VDS and VGS here. VS can be avoided. So you can directly take it as 10 minus 10 Vi should be greater than or equal to 3.9. What was VT value? VT was given as 0.7. So 3.9 plus Vi minus 0.7. So if you solve, you will get it as Vi should be less than or equal to, Vi value should be less than or equal to 0.618 volts. Vi should be less than or equal to 0.618 volt, or it is 618 millivolts. Your input signal cannot be more than 618 millivolts. So if you have any doubts, you can ask. Is this clear? Is this numerical clear? Oh, it will take some time because this is the first time you are working on a numerical with a lot of steps like DC analysis. You have to get some parameters, then you have to go for AC analysis, right? So it will take some time. So I request you to practice this numerical and understand this properly, so that if you get another variety of this, you will be able to solve. 2.4. Yeah, I got the answer. So can I move ahead? Go ahead, or you have some doubts here?
Excuse me, sir.
Yes. Yes, Praveen.
Sir, how did you take that minus sign, sir? Minus mod of A into Vi?
Yeah. Are you clear with this equation?
Yes, sir.
Yeah, then you can go ahead with this. What is the A value in this question?
Minus 10, sir.
Minus 10. Yeah. So if you substitute minus 10 here, directly you will get this equation only, 10 minus 10 Vi.
Oh, correct, sir.
Right, or you can, so it is with the understanding that if you have input signal increment, if your input signal is growing or in the positive direction, if you have an increment, output is also getting amplified, but you are getting in the opposite direction first. So just to accommodate that, either with understanding that when your input goes plus, your output will go negative, that can be one thing, or when your input goes positive, your output will also go positive, but A is negative. So here it is accommodating. So that negative sign is accommodated there. So you can write in either ways. Is that clear, Praveen?
Yes, sir.
Okay. All right. So if you have doubts, please ask. Meanwhile, I'll quickly go to one more very important and interesting topic. So it is about calculation of small signal output resistance. So what is MOSFET's small signal output resistance? Is it possible to find out the output voltage independently? What is the meaning of that, Kirtana?
So it means can we just find out the gain, or is it possible to get the output voltage separately?
I didn't get that again. Is it possible to find gain is what we obtain, right? AV and
Yeah.
AVS are gain, yes.
We can we find out an output voltage also, provided an input voltage should be given, right?
Yeah, input should be given and gain also should be there. Then only you can write the output,
Yes, sir.
right? So is that you expected or you have some other doubt?
No, sir. Like we found out maximum input voltage, right? So
Yes,
is there
yes.
some maximum output voltage or something like that?
Maximum output voltage, see, we can actually limit when you talk about maximum output voltage, the output maximum can go even the supply volt, even it can go till the supply limits. But the question is, or but the problem is, whether and at that condition whether the transistor remains in the proper region of operation or not. So in order to bring that condition, we have to force on the input side. So when you're
Basically,
giving,
we
yes,
had a intrinsic gain like minimum like what is the maximum gain we got to know that
yes,
GMR. So
yes,
so using that can we find out like the maximum output or something like that? I had
yeah,
an
yeah, we can find that. But again, when you look at this numerical or this problem itself, see if you look at this question, in this question you have what to say, yeah, you have actually intrinsic gain is contributed by gm r naught. R naught is a small signal resistance of the MOSFET. But in this circuit we cannot say that even though intrinsic gain is gm r naught, that gain is not available. Why it is not available? The gain available is not gm r naught, the gain available is gm into r naught parallel rd parallel rl. So gain itself is reduced from GMR0. That is why we stated that the maximum gain possible is GMR0. But for various reasons, you will not be able to get gain as high as GMR0. So now if you look at this, your gain is smaller than GMR0. It is GM into R0 parallel RD parallel RL.
yes, sir. Got it.
So finding a maximum voltage by considering GMR0 will not make sense here because GMR0 itself is not available in the circuit.
Yes, 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 sir.
Okay, yeah. Thank you, Kirtana. That's a good question. Okay, so let me quickly go to this how to calculate the small signal output resistance. So the question is why we need to calculate small signal output resistance. So I will start that with calculating small signal gain. What is small signal gain? Whatever we have written just now, V out by V in. But this V out by V in can be written as V out by I out into I out by V in. Is it possible? V out by V in can be written as V out by I out into I out by V in. Now, if you look at V out by I out, what will be this V out by I out? How can I call this ratio? It is V by I. Since it is V by I, it is resistance. Now, since it is measured at the output, since output voltage and output current are given, so this can be called as R out. Similarly, this ratio is I by V, so it is conductance G. Now the one current is measured at output, voltage is measured at input with the, so that is a trans conductance. So we generally call it as GM. Right. So for any circuit, what I have written now is for any circuit, gain can be written as the product of GM and R out. Where what is GM? GM is trans conductance of the circuit, not of the transistor, but of the circuit. Trans conductance of circuit, and this is output resistance of the circuit. Now this makes this is actually a shortcut to write the gain of any circuit. So we will find GM separately, we will find R out separately, and then we will combine it to get the gain. So gain can be written as AV can be written as GM into R out. Is that clear? Can I get some response in chat box? There are 57 people. If it is not clear, you can throw questions now. All right, yeah, I'm getting few response. Please let me know whether you are understanding or not. So depending on the pop-up responses coming, I will be thinking that yes, you guys are with me. Even if you are taking some time to understand, that is perfectly fine. Go through the video and come back again. Now, so to find R out, to calculate R out, if you follow certain steps, we can find the output resistance of any circuit in a systematic way. So that is what I'm going to explain now. The first step is we should nullify the effect of all the other sources. So I will write all the other independent sources. Again, the question is how will you nullify the effect of independent sources? Then I have to make it clear. If it is a voltage source, you can nullify the effect by keeping a short. Yes, Madhusudan, I have seen your query now. Is R load equal to R out? Not exactly, because see, for this question, if I look from this side, if I look from the output side, I can see three resistance in parallel. RL is the load resistance what we have added, or RL is the load resistance of the circuit. But the output resistance is not only that. You have other two more resistance connected in parallel. So sometimes we will measure output resistance by excluding the load resistance. Sometimes we will include the load resistance. But the output resistance is not only load resistance, the other resistance which are coming at the same terminal also need to be considered. I hope that is clarified. Can you respond, Madhusudan? All right. Okay. Now, so to nullify independent sources, voltage sources should be short, and if there are current sources, that need to be open. So this is your first step. So this independent sources can be either AC source or a DC source. Whatever it is, if it is independent, you can short it and you can open it if it is a current source and an voltage source. Here mostly it is referring to DC, but even if you have an AC source as independent source, you can make it open. Now the second step is apply a test voltage. So after this procedure, I'll explain how to calculate that. So apply a test voltage V test at the output node with a current I test. That is the second step. And third step is evaluate what is V test by I test and mark it as R out dash. Right. So I will explain that here. Say for example, you have a circuit. We do not know what are the components present inside. So only one thing I know, there is a load resistance connected here RL, and there are input is also connected at the inputs this side. Right. Now, based on the steps what I have told now, first thing is we have to nullify the effect of all the independent sources. So if you are seeing the independent source V in, what we have to do is we have to nullify this. That means I have to make this short. Second is you have to apply a test voltage. So I have to apply a test voltage here. I'll mark it as V test, and this is the current I test. And then whatever is coming, whatever measurement I am getting, I have to mark it as R out. So what I will do first is, if I look at this RL resistance component, you can see that this RL is coming in parallel to this voltage applied V test, right? So now when I find V test by I test, I will get the entire resistance of the circuit. You can see that this RL is anyway in parallel to that. So what we generally do is we will keep RL separate, and then we will do this measurement V test by I test. We will mark it as R out dash, and then as a fourth step, we will write the final R out as the measured R out dash in parallel to RL. Why am I doing this? Because RL is anyway connected in parallel to the test voltage and the test current. So I will keep this RL aside, do the measurement, and then I'll take the value in parallel. So your R out is R out dash parallel to RL. Is this clear? Whether the steps are clear, I'll explain you how to do this calculation, whether the steps are clear or not. So in order to find output resistance, we have to nullify the effect of all the independent sources first. Then you have to apply a test voltage with that current of I test, and then measure that as R out dash, and finally add that in parallel, add in the sense combine it with the load resistance RL. Now you will not understand this, these are only the steps. Let me explain with one simple case. The first case is you have a transistor where gate is connected to a DC bias. You are asked to find what is R out from this side. given that lambda is equal to 0. Right, this is a very simple case. Probably you will be knowing. Can you tell me what is the output resistance here? For a MOSFET, if lambda is 0, can you tell me what is output resistance? Infinity. It is infinity. But I'll let you know how to do this. So in order to do this, since lambda is 0, I will take the equivalent circuit. So equivalent circuit is, if this is GM-VGS, and if this is VGS, that will be GM-VGS, and these are the three terminals. This is what I know about the MOSFET. Now to input side, what is given is V bias, and this is what I need to find from here, R out. So what is the first step? As I explained before, the first step is actually to nullify the effect of all the independent sources. So you can see an independent source here, V bias to bias it. So you have to nullify that. That means I have made it short. Now when I made this short, what is VGS? Your so this is also ground because your source is ground. So when you made this source, your VGS is 0. Now if your VGS is 0, what will happen to this current? This current source is not there, because since VGS is 0, GM VGS is also equal to 0. Right. Oh, sorry, I forgot the first step. So what I should do first is I should actually connect test voltage V test, and which is carrying a current I test. Right. So first I nullified the effect of the independent source, then I made the modification accordingly, then I connected a test voltage. Then now I want to measure what is V out by, sorry, V test by I test. What is I test here? Since it is an open circuit, I test is equal to 0. So what is V test by I test? That is your R out. This is equal to, V test is some voltage what I applied, but since I test is 0, this is infinity. Right, your R out is infinity in this case. So there is no RL, there is no other resistance connected here. That is why we are not finding R out dash and then RL, we are directly finding R out. So this is your ideal MOSFET. So ideal MOSFET, and your R out is equal to infinity. Now second case is, you consider one more MOSFET. This is V bias. This is same R out you have to find, but lambda is given not equal to 0. So what will you do in this case? In this case, we will start with the same equivalent circuit. So this is GM VGS. This is R out. This is what we know about MOSFET. I have replaced the MOSFET equivalent circuit with this. Now I should modify this accordingly. So here it is given that V bias, but we know that in order to measure or in order to calculate output resistance, first we have to short this, because independent sources should be nullified. I have done that. Source is also ground. That means your VGS is equal to 0. That will make this as an open circuit. Right. VGS is equal to 0. GM VGS will be equal to 0. Now if I connect a test voltage here with the value of V test, with this as I test. What is I test, or what is V test by I test? So this is 0 anyway. So your V test will be equal to I test into R naught, or V test by I test, which is equal to your output resistance is equal to R naught. This we already know, but I have taken the same example to clarify or to explain or elaborate the procedure. Now this can be, so this is non-ideal MOSFET. This is non-ideal MOSFET, and this R out is equal to R naught. Right. Now this can be elaborated, or this can be used to any circuit of MOSFET to find the output resistance. Right. So we will look at few more examples. So before looking at other circuits, we will look at few more examples, and with those examples we will find, or we will get practice with how output resistance is calculated, and then we will go for other circuits. Right. So probably with the two or three examples, I'll send you a very short video of 10 minutes to how to calculate the output resistance, and with that we will finish this output resistance calculation. All right. So if you have doubts, you can unmute and ask now. Otherwise, we will meet next class.